All right, so today's going to start out with a discussion of hydrolysis reactions, which are really just addition reactions in reverse. So let's take an example. We said we could make these cyclic ketals, and why are these useful? They're protecting groups for aldehydes and ketones, right? And then we said if we wanted to remove this protecting group, all we had to do was basically hit this with a lot of water and an acid catalyst. And if we do that, we'll end up with our ketone plus our original diol. So previously, we saw how to do this direction, but we really haven't practiced the removal process or the hydrolysis, right? But the mechanism, luckily, is pretty straightforward. Only downside is it's just as steppy as putting it on. So let's try to make sense of the mechanism. All right, so we're going to start out with the exact reagents I have shown above. Look like this. We've got water, and we've got our acid. I'm just going to put the acid as a proton in brackets. And we know under normal conditions, this is equilibrium, or under equilibrium conditions. However, we can show this as a one-way arrow if we assume excess water. So if you do want to just save time and skip the equilibrium arrows, you can show it as a one-way arrow because we're pushing it with Le Chatelier's principle, right? So first step, what do you think is likely to occur? Got acid around, acid-base chemistry super fast. Where will we protonate? One of the oxygens. Probably not the water because that doesn't lead to any sort of forward progress. However, we could protonate one of these oxygens. All right, at this point it's kind of nice because if we think about it, this whole group is a decent leaving group. It's a good leaving group because when it falls off, it's neutral, right? So we can show this a variety of different ways. You can either showing it falling off in one step, or you can show it being shoved off. I'm kind of a fan of showing the shoving off. So the lone pair from this oxygen will kind of clamp down and kick off that leaving group. Doesn't really matter which way you show it though. All right, we still have water hanging around, so I'm going to show that over here. And then when we think about it, the product that we just made now has an oxygen double bond. We still have those two carbons, and now we've got this OH group. And we also have water floating around. What am I forgetting though? I need a plus. I need a plus on this oxygen, right? This is resonance stabilized, so you could show both resonance forms. Doesn't really matter. I just happen to choose this one. So unless I say show all resonance forms, you're welcome to pick either. All right, so we're getting there. What do you think the next step is going to be? Yeah, water is a decent nucleophile, and because that oxygen has a positive charge, that carbon underneath is incredibly electrophilic. So you could show this attacking in, kicking up electrons. So now we've got our water added in. That looks pretty good to me. Kind of thinking backwards though, we want to ultimately try to get rid of this entire group, but it's not a very good leaving group. What should we do in our next step? Yeah, maybe get that oxygen down here to have a proton. And we can just move the protons around, right? So if you want to, even on an exam, you can show plus minus H plus to basically indicate that one of these protons coming off that positively charged oxygen is going to get shuffled over to that other proton. So just like we saw before, we can show proton transfers. Typically that's facilitated through the solvent. Just like before, this is a good leaving group. And if you've got a good leaving group like that, that's a terrible G. Let me fix that. If you've got a good leaving group like that, you can show this getting essentially shoved off. Now we've completely kicked off our leaving group. And very last step, what do you think is going to happen? Deprotonation. What I tell my students every year is you should be able to do this forwards, backwards, upside down in your sleep, spin around 3 times and then do it. A good test is to honestly try to add in the arrows going in the opposite direction. So if you wanted to, we could go from this end back to the beginning and we could ask ourselves, well, what's the first step going to be? And then make sense of it and be like, well, this makes sense. We're going to add a proton onto that carbonyl and kind of work backwards. So really test yourself on this. Your problem of the day that's due tomorrow is pretty similar to what you're looking at right now, but trust your acid-base chemistry. Trust the trends that you've been seeing and make sure that you can master going in either direction. These look pretty intimidating, but really a lot of it's just similar arrow pushing that you've seen all chapter long. Does that make sense? All right, so that's pretty useful. Like we said, you can protect ketones pretty easily this way, but this also works for imines and enamines. So let's take a look at what this looks like if we were to have a nitrogen nucleophile instead. So first of all, is this an imine or an enamine? It's an imine. So if we want to pop off that imine, same thing as before, we're going to add excess water. We typically use some sort of acid catalyst. And when we do that, we're going to convert that imine into a ketone in this example. It also works with making aldehydes. And then in this case, we're going to get our primary amine, right? So we can just flood this with water and take advantage of that. If we have an enamine, same sort of thing happens. Where we have H and R2, so we have our secondary amine in this case. So either of these we can do. Which mechanism do you want to try? You want to do the imine hydrolysis or the enamine? Does anybody have a strong preference? Enamine? All right. I thought that's what people would say, so that's what I have in my notes. That's good. All right, so let's try this with an enamine. Like I said, we have our acid around, and we also have our water around. That's kind of our mixture in solution. We know acid-base chemistry will take priority. If we protonate water, just like before, that doesn't take us in any sort of forward direction. So now we've got to decide where the most basic site is on our enamine. Yeah, so a lot of people are really tempted to show the nitrogen, but if you protonate the nitrogen, it doesn't really take you anywhere, right? Where's the next best protonation site, though? Okay, so the carbon double bond, we know we can protonate those. So let's see how this can kind of get us going in a forward direction. in this case, we're going to end up with our positive charge on the more substituted carbon. Why? Carbocation stability. It's on a highly substituted carbon, stabilizes it. What else? Resonance, right? So it's resonance stabilized. So that's a good thing to have. All right. Now we also have water floating around. What would occur in this next step? Yeah, the oxygen can attack in. You see how if we had protonated the nitrogen, we wouldn't have the ability to add in water. It would just kind of look at it. All right. So now we can add water in. That kind of starts the whole hydrolysis process. Let me actually slide this over a smidge. I'm going to just do that to piss off Ian now. All right. So what would the next step be? We know our ultimate goal is to get rid of this chunk, but it's not a good leaving group. Yeah, shift protons and try to protonate that nitrogen. So I'm going to show a plus minus H plus, moving a proton from that alcohol over to the nitrogen. Yeah?
If I was actually doing this reaction, how would I just keep the water fall back off?
That's a good point. Under equilibrium conditions, will it fall back off? Absolutely, right? Yeah, so we're trying to, I'm showing this with one-way arrows because Le Chatelier's principle is going to push this ultimately towards completion. Yes, but the idea of it being reversible is 110% true. Not 110%, 100% true. All right. So now we've got ourselves set up. We've got a proton on that nitrogen. We've got these two R groups. So now this is a good leaving group. And just like we saw before, the lone pair from this oxygen can clamp down and shove off that leaving group. The number one thing I will say is do not memorize this. I've seen students where they try to brute force memorize these. You will make your head spin. Try to understand why you're doing each step, because then you can apply it to any situation, regardless of how comically crazy it looks. All right, so we're almost there. Last step would be what? Minus H plus. And in this case, what's the best possible base around? The lone pair on the nitrogen. However, if you show minus H plus, I'm perfectly fine with that. And in many ways, I like just showing it as minus H plus. That way I can practice my forward and backwards arrow pushing. So just like before, if you wanted to do the backwards arrow pushing, again, you could go backwards just by adding in the arrows going the opposite direction. So that's a really good way of checking yourself. Does that make sense? All right, I think I'm going to skip the imine just because it's kind of the same iterative process over again, but make sure you check your work and make sure that you feel comfortable doing this. Like I said, trust me, when you look at the problem of the day, you'll be like, what's this? But trust yourself. Trust the basic arrow pushing that you've learned. All right, there's a handful of other nucleophiles that we need to look at too. So we'll start out with sulfur. Sulfur, as we saw way back in first term, is a really, really, really good nucleophile. Why is that? Why is it better than an oxygen nucleophile? Yeah, it's less electronegative. So because it's less electronegative, it's going to behave like an amped up alcohol in terms of its nucleophilicity. So in this case, if we have two equivalents of our thiol, and we have catalytic acid around, it's going to behave just like an alcohol. Where instead of oxygens, you just have sulfurs, right? Makes a lot of sense. And then in this case, we're going to kick off water. We could practice doing the reverse reaction too, the hydrolysis. It's going to behave really similarly to what we've seen before. All right, this is just called a thioketal. So instead of calling it a ketal, we want to differentiate it because it has sulfur, so we just throw in the thio to indicate that it's the sulfur analog. Additionally, what we can do is the analogous situation where we have two thiols. This looks a lot like what we did with alcohols too. Where you make that cyclic system. So this would be a cyclic thioketal. And you might be thinking, why? Why do this if we can protect our ketones with oxygens? Especially if you're a chemist and you saw a bottle of that, you would want to plug your nose. This stuff stinks to high heaven. So why on earth would we ever want to use this? Because you have a coworker you hate? I suppose that would be a reasonable thing. Yeah, that'd be a cruel trick though. Really, the big benefit of this is this next reaction. So I'm going to write this down. Why is this useful? All right, so let's take that cyclic thioketal that we just made, and I'll show you a super cool trick. You can take this plus something called rainy nickel. And you can convert it all the way down to the alkane. It's pretty cool, yeah. So let's take a look at what rainy nickel is. It's called rainy nickel. I don't exactly know why. I'm assuming after the scientists that worked with it originally. But it's a spongy nickel aluminum alloy. Ugh. With hydrogen absorbed. This is getting into super duper advanced chemistry, and to be perfectly honest, our book doesn't show the mechanism. I'm not going to show you the mechanism, but if you're interested, I can try to pull up the literature showing how this mechanism proceeds. For the most part, this book's really good about showing mechanisms, but some of it is just way beyond the scope of this course. So this reaction, where we originally start out with a carbonyl and we end up with an alkane, we've actually seen before, right? So let's take a look at all of the different ways we've seen this. So does anybody remember the name of this one? It's a Clemenson reduction. All right, so that one kind of did a similar thing. There were some limitations to this. You had to have an aryl ketone, meaning you had to have an aromatic ring attached directly to the ketone in order for this to work. And then the other thing that was kind of limiting was you had to have acid around for this to work. So if you have any sort of functional groups that are acid sensitive, you really couldn't do the Clemenson reduction. All right, there was another one that we saw. I'm going to just make this a non-aryl ketone because this one will work for any sort of ketones and aldehydes. And this one was a bit more complicated. In step one, let me make this bigger even. We did this, and if you remember, this had to be pH controlled, so I like to show a little star underneath it to say that it's not just any regular acid, it's actually under buffered conditions. So in that first step, we made an imine, and in the second step, we can treat this with sodium hydroxide, water, and heat. And we can accomplish the same sort of thing where we get rid of the double bond. All right, So this works with any ketones or aldehydes. Oops. What's a potential drawback, though, with the reaction conditions? Think about what I circled above. We said it was problematic because you might have a functional group that's sensitive around acids. Yeah, what if we have a functional group that's sensitive around bases? In this specific example, we didn't, but if we're working with a complicated organic material, we might. All right. The one we just saw would also work for this reaction. So we've got our conditions through which we can make a cyclic thioketal. And then we can treat this with Raney nickel. And we can get rid of it this way. This one's nice because it works with any ketone or aldehyde. No, this one's not as sensitive because thiols typically aren't super duper strong bases like amines are. All right, so this one we don't have any sort of crazy strong acids or bases to get it to go. It'll work with any aldehyde or ketone. What's the one potential logistical drawback? I mentioned it previously. It's super stinky. So this is one thing that always bugged me, where I was like, why do we need 3 different reactions to accomplish the same thing? Sometimes it depends if you have acid-sensitive functional groups or not. Sometimes it depends if you have base-sensitive functional groups or not. Sometimes it depends if you're willing to work with something super-duper stinky or super-duper toxic. It's kind of different pathways depending on the circumstances you're working with. This works really well and is actually a fairly green reaction too compared to some of the other ones. Make sense? All right. So let's move on really quickly and review hydrogen nucleophiles. So let's think about it this way. Oops. Let's say I've got an aldehyde, and my goal is to add in some sort of new nucleophile that's a hydrogen. How can I accomplish this? LAH? I'll just actually write it all out, LiAlH4, or what? Okay, so if you do this one, you would need water. Alternatively, you could do NaBH4 and something like methanol, and that would work really well. In fact, we've seen this a handful of times already. And we can do the similar thing with ketones. Where we can add in a hydrogen nucleophile a couple different ways. And really, this is just review from what we've seen before. We can do this with lithium aluminum hydride, followed by a water workup, or sodium borohydride and methanol. We didn't really think about this in the same way we've been doing the other reactions, but in reality, it's the same sort of chemistry, right? You've got hydride, which is like H-, it attacks into that carbon center and goes from there. Hydride is such a good nucleophile in lithium aluminum hydride and sodium borohydride that we don't need to protonate this oxygen in the very first step. It'll attack in first, and then we protonate it after using our water or methanol. So it is a lot more aggressive as a nucleophile because it has a full negative charge and is relatively unstable. Does that make sense? All right, last one. Or I shouldn't even say last one. Second to last, for today at least. It's carbon nucleophiles. We've seen carbon nucleophiles too for aldehydes and ketones. So let's say I want to do this. In fact, let me color code this. How can I accomplish this transformation? We've seen it before. Grignard reagent. So we could do a Grignard reagent and then quench this reaction with water. Really, that's a carbon nucleophile too. We've seen it. We're pretty comfortable doing it, I hope. So pretty straightforward, but there are some new ones presented in this chapter that we haven't seen before. The first one is called a cyanohydrin. This comes into play more when we get into carbohydrates. We'll see this in the carbohydrate chapter. Like I said, carbohydrates are really just fancy aldehydes and ketones. You don't see this a lot for synthesis outside of carbohydrates. But let's take a look at it. And we'll do our best to figure out what's going on. So in this reaction, we're working with potassium cyanide. So that's the cyano group, right? What do you think is going to happen? Yeah, so cyanide's going to attack in. We don't have acid around, meaning we don't need to protonate the oxygen first. The carbon with the negative charge is a good enough electrophile on its own. And in fact, I would highly suggest not doing this in acidic conditions. Why? We'd make hydrogen cyanide and kill ourselves. We don't want to protonate that cyanide, right? We want to keep this under basic control to avoid accidentally killing ourselves. That's just a practical tip in life. Avoid killing yourself if possible. All right. So now we've got this nitrile added in. Just like before, we're going to protonate it using some sort of acid after that step, so through some sort of workup. And we're getting there. Once we're at this point, this is called a cyanohydrin. And we can actually isolate it and work with it. We're not going to look a whole lot at this right now, but I will kind of give you a sneak peek of what we will see later on in the carboxylic acid chapter. So the sneak peek that we'll learn later is you can actually do a couple different reactions with this. The first one is to treat it with LAH and water. And we'll look at this reaction when we cover nitriles. It's a different chapter in our book. But essentially that does nothing to the alcohol portion. It only reacts with the nitrile. And you can reduce that nitrile to an amine, which is kind of neat. So it's going to add in hydrides essentially there and there, almost like we would to an aldehyde or a ketone. So it's kind of neat. We'll take a look at that later, though, when we hit the chapter on carboxylic acid derivatives. And then the last one, we can treat this with acid. So dilute acid and heat. And we can actually convert that nitrile group to a carboxylic acid. So again, we'll see this when we get into the carboxylic acid chemistry chapter. But really, as far as I'm concerned, I want to see that basic nitrile addition to a ketone or aldehyde and then just stop at the cyanohydrin. We'll get back to this later. Does that make sense? So I'll just put a little note here. We'll cover later. So I'm not purposely trying to skip the mechanisms. I'm just saving it for a chapter. All right. The coolest one is a reaction called the Wittig reaction. And so I'll really briefly show you the overview, and then we'll jump into the mechanism. This works with an aldehyde or a ketone, so let's make a note of that. And we're going to use an exotic new reagent. Like, there's too much going on here, stop. All right, this is called an Ylide with a Y.
That makes it all much better.
Yep. Right? So this is a really, really reactive reagent, right? Why? Think about it. Carbon with a negative charge. This looks like a Grignard reagent, right? So this is going to actually attack in. We'll go through the mechanism here in a second. But after it adds in, what happens is you will convert that carbonyl group into an alkene. And normally, it's the Z isomer. So if you remember Z same side for assigning the stereochemistry, same thing here. It prefers the Z isomer, which is a bit unusual. Yeah?
So with the Ylide, so does the negative charge of the carbon counteract the sheer size of the three phenol groups attached to it in the reactivity on this?
Yeah, so if we think about it, you might actually see this drawn a different way. So let's think about this. So let me redraw this. It's kind of double bond and single bond like, just like sulfur. Phosphorus isn't great about following the octet rule, right? If you remember phosphoric acid, that doesn't even look like an octet. This phosphorus, neither does this. So in this case, you might see it drawn either way. I personally like showing it with a negative charge because then it emphasizes that that carbon is the thing acting as a nucleophile, where with the double bond, if you're not familiar with electronegativity trends, it's not immediately clear if the phosphorus is the nucleophile or the carbon. But carbon is more electronegative than phosphorus, so it's the thing carrying that negative charge in this case. Does that make sense? The other thing to think about too is, why is this positive charge so stabilized here? Resonance, right? It has 3 aromatic rings stabilizing it through resonance. So even though it looks really unstable with that positive negative zwitterionic formation, it's actually quite stable that way. Those are good questions. So let's take a look at how we make the Ylide, because normally we don't just buy it. All right, so first thing, whoop, this should be a phosphorus. First thing is we need triphenylphosphine. And then we need some sort of alkyl halide. And in this reaction, we know that the alkyl halide can do substitution chemistry. And in this case, it's a primary alkyl halide, so is it going to be SN1 or SN2? SN2. So this will come, attack, kick off our leaving group. This really will only work well with a methyl or primary alkyl halide. Why wouldn't it work, let's say, with a secondary alkyl halide very well? It's too big. You're carrying around 4 phenyl groups on your nucleophile. You're going to run into steric problems if these get too bulky. So it can't be too bulky. I'm just going to keep these as pH groups to keep things somewhat sane. And at this point, phosphorus has a positive charge already. All right, we know that our leaving group's still floating around. If you want to show that, you can. It's really just a byproduct at this point. And at this point, we're close to our ylide, but we're not quite there. If you think about it, right, we have one too many protons coming off there. So we need to rip off one of these protons, and we need to select an appropriate base. That's actually a pretty hard proton to rip off, so we have to get a very strong base in order to remove it. All right, so the one that's most commonly used looks like this. So this over here, right, is a butyl group. This is called butyl lithium. So another way of writing this is BULI. It's a lot easier to write BULI. It's just short for butyl lithium. It just means you've got a butyl group and a lithium, and you've got a negative charge on one carbon, and your lithium is your countercation. So in this reaction, it's going to immediately go after the most acidic available proton, which is the one I've highlighted. I'm going to clamp down. Oh, that looks like an H. And now this carbon has a negative charge and a positive charge. So this is our ylide. And like I said, you can actually see this written two different ways. Sometimes you see it written with the double bond. However, these are referred to differently. If you see the double bond version, this is called a phosphorane. So you might see that terminology thrown around. In general, I just refer to them both as ylides because why have different names for the exact same molecule? So I just wanted you to be familiar with the different name if you saw it. All right, so let's take a look at the overall mechanism for what the heck the ylide does in the presence of an aldehyde or a ketone. And then we'll call it good. All right. So I'm going to kind of spin this around so that the carbon end is facing our ketone. Doesn't really matter. But just like we saw with the Grignard reagent, this carbon with the negative charge is going to slam into that electrophilic carbon on our ketone or aldehyde and kick up electrons. So pretty intuitive at that point. All right, so this carbon over here still has that hydrogen, still has that R group, still has this phosphorus, and it still has 3 of the phenyl groups coming off of it. Does that make sense so far? So it's just that addition product. All right, the cool thing with this is that oxygen is right next door to a positive charge. So it's actually just going to swing over and find that positive charge. Electrostatics are driving this, right? Positives attracted to a negative. It's pretty convenient and actually helps stabilize this intermediate. So this intermediate is called a betaine. I'm not going to quiz you on all of the weird names of the intermediates, but I do like showing them in case you see it written in the textbook, you know what the heck they're talking about. And this betaine, because that negative charge is so close to that positive charge, tends to form a 4-membered ring. People look at this and they're like, isn't that unstable? Yes, it is unstable. Just like I said, I like people to know the names of these intermediates in case they run into them. This is called an oxyphosphatane. So if you're playing Scrabble, I actually got angry once. I played Scrabble with my grandma and tried to use a chemistry word, and she's like, that's not in the Scrabble dictionary. I'm like, but it's a word. Needless to say, she beat me. All right. The last step is this is ridiculously high energy. It does not want to stay in this four-membered ring orientation. Instead, what happens is this weird process where one of these one of these sigma bonds will jump over, and the other one will jump over. So it's kind of like a cyclization. It's a bit weird. So underneath, we're forming a carbon-carbon double bond. See how that's kind of that bottom portion? And then up above, we're forming an oxygen-phosphorus double bond. So we end up with these two products coming out. This one is our new alkene. And then this chunk that blew off right here is remarkably common in advanced organic chemistry classes. This is called triphenylphosphine oxide. What's that? Yeah, it's just natural, right? So triphenylphosphine oxide is notorious in organic chemistry because it's a thermodynamic sink. Once you make it, it's like brick dust, and it will not do any sort of reverse chemistry on you, which means it's really nice because it'll drive this to completion. So let's just write that down under here. Was there a hand? Yeah, you figured it out? Okay. So like I said, the alkene that we normally make here is normally the Z alkene. So it's a pretty cool reaction to convert a carbonyl group, meaning a CO double bond, into any sort of alkene that you want. I think it's kind of neat. All right, so we have a couple minutes left. I wanted to show you one basic problem-solving strategy. All right, so here's the situation. My goal is to make this molecule. So the question is, what chunks would I need to make this molecule? And there's actually a couple different ways. So for example, maybe originally this chunk was my ketone. Right? That would make sense because then we could say, all right, maybe that was my ketone. And then maybe over here, maybe this part was my Ylide. All right, if that was my Ylide, what would that look like? We need to account for every single one of our carbons. So we still have 2 carbons coming off there, which means this must have been a triphenylphosphine group, and that carbon must have been a negative charge. Does that kind of make sense? The number one mistake I see students make is they forget to include that carbon and have the phosphorus right there. We need to account for all of our carbons from beginning to end, so don't neglect that carbon. All right, so that's one option. Or let's do it the other way. Maybe this whole chunk was an aldehyde, and maybe this was our Ylide. And so let's think about our Ylide, what that would look like. So our Ylide in this case oops, I forgot my positive charge here. Would look like that, right? So that carbon would add in. And then our ketone, or aldehyde in this case, excuse me, would look like that, right? You guys kind of follow along how both of these could theoretically give you the same product? Which one would be better, the top one or the bottom one? Well, think about it this way. This is our nucleophile in the top one. This is our nucleophile in the bottom one. They're really similar. They're carbons with a negative charge. What else impacts nucleophilicity? Sterics. Which one's the better nucleophile? Top one. So when you are working through these problems doing retrosynthesis, oftentimes there's multiple ways, but if you can, try to pick your nucleophile that's least bulky, because that's going to be the preferred pathway. You'll get more of your product. Yep?
Can't you also just say the top because when we were going through how to make it, you said that it only works with the methyl or...
Yes. So I said really the best way to make an Ylide is to choose a methyl or primary one, and that again gets back to this point that we don't want our Ylide to be too bulky or else this reaction gets really sluggish or just won't work. Yep, so that's where we'll stop today. For the exam, we won't go past the Wittig reaction. What I'll do is I'll go into sapling and I'll pull problems about the Baeyer-Villiger oxidation. If you want to read ahead, you can look at that. We'll just cover that after our exam.